Okay, good afternoon, everyone.
Good afternoon.
Back into it, yes? Related rates? All right. So we're gonna do, it's not gonna be a quiz, but I'm gonna give you a poll. I'm gonna give you two questions, just to get us warmed up here. So let's take, I don't know, I don't wanna go more than maybe 6 minutes on this. Just see what you can do. I'm not gonna take this for a grade. I'll launch the poll here. The poll says that it's a quiz, but don't worry about that. So I just wanted you to take the derivative with respect to t on both of those equations. One more minute. If you came in late, I'm not taking this as a quiz grade. This is just for practice. All right, let's talk about this. Let me share the results of the poll here. So for question number 1, 93% of you said it was D. And for number 2, 73% of you said it was C. That is correct. Those are the correct answers. So D here and C here. So let's just run through these real quick. All right. The first one there, we're going to take the derivative with respect to t here. So we have to do derivative both sides. So the derivative of v with respect to t would be dv dt equals, now on the right side, everything in yellow is a constant. 4/3 is a constant, pi is a constant, so that will just come for the ride. And then all I really have to worry about is differentiating r cubed with respect to t. So that's a chain rule. I have to do the r cubed first. So I bring out 3 and then r squared. And then I have to take derivative of r itself, which would be dr dt. And the 3's cancel. So you get 4 pi r squared dr dt, which is this, equals dv dt. Now on the second one, the tricky part was this 1/x, but I gave you a hint. I reminded you that 1/x means x to the -1. So if we differentiate the left side, we have to take first the derivative of tangent of something, which is secant squared of it, right? Secant squared of theta. But then chain rule says times the derivative of what's inside. So you have to take the derivative of theta with respect to t, which is d theta dt. Chain rule, right? And then that must equal on the right side, if you look at this as x to the -1, you have to use power rule. So -1 comes out, x to the -2 power, times, now again, you have to take derivative of the base, the derivative of x with respect to t, which is not 1, it's dx dt. And then you could rewrite x to the -2 as 1/x squared, which is where we get this from. Any questions on those? Okay. All right, let's talk about our schedule real quick. I think I was talking to some students at the end of class last time about this, when our next test is going to be. We are not going to wait till November 25th to have our 3rd exam. I'm thinking a good place to put that would probably be in like 2 weeks. Maybe 2 weeks from today, the 4th. And then, you know, we'll know a little more by the end of next week where we are. But my guess is that would take us through, probably through 3-3 next week. And so that's what would be on the test. Maybe a little bit of 3-5, we'll see. But let's plan right now to make November 4th, our 3rd exam. All right.
All right.
All right. So now back to related rates. So I gave you all this sheet, I sent it to you. It's in your course files. I think I put it there also. Maybe I did. I don't know. But we were doing these notes and I want to continue here working these examples. So Let's see if we can get through this first one. We have an expanding sphere. Last time we had an expanding circle. So now a sphere is three-dimensional. And this is an example of a sphere that expands where its radius increases at a constant rate. So it's hard to see in this animation, but I'm going to start playing it. If you watch this sphere grow, this is three-dimensional, you can maybe tell that the radius is growing at a constant rate here, but the volume is not. And you can see how quickly the volume starts to grow, starts to really start moving here, where the radius is just consistently growing at the same rate the whole time. So the question here is this. Let me go and bring that over here. I'll slap it in here. If the radius of a sphere is increasing at a constant rate of 2 feet per second, as soon as you see feet per second, you should be thinking, oh, well, that's a derivative of something. That's the rate at which something is changing with respect to time, right? So the radius, right? The radius is increasing at that rate. How fast is the volume? So what we're looking for is how fast, the derivative, right? Again, fast is a speed. We want to know the derivative of the volume, right? How fast is the volume increasing when the volume is exactly 36 pi cubic feet? So this thing is growing, and exactly the moment that the volume is a certain thing, 36 pi, at that instant, we want to know how fast the volume was increasing. So let's start putting our information together on this table, or filling out this thing. So my general picture, I'll start with that. I've got this sphere. Good way to draw a sphere is to draw a circle and then draw almost like a little, almost an ellipse looking thing in the middle of it like this. You can kind of get that three-dimensional feel to it. Put a center. Now this thing is growing. So the radius here, R, I'm going to call it R. I'm not going to fix it because it's changing. So I've got this sphere, it's growing. And then the specific moment in time where we're talking about, we've got the sphere. But now what do I know at the specific instant? What is the information I know? How fast is the volume increasing?
5 feet cubed, and the radius is increasing at 2 feet per second.
I'm sorry, I couldn't hear in that. You sounded real far away.
It's increasing at a rate of 2 feet per second, and the volume is 36 pi feet cubed.
Yes. So, but at the instant in time, right? Like, because remember, when it's growing, when we talk about the instant in time, we're almost like freezing it. So at that instant in time, when am I freezing it? I'm freezing it when
Volume is 36 pi.
the volume hits 36 pi cubic feet, right? That's when I'm freezing it. So in this picture, what I know is that the volume is fixed to be 36 pi cubic feet. That's it, right? So the difference between these two pictures is that in this one, it's growing, and on this one, it's fixed at a certain, well, it has to have a fixed radius now, doesn't it? Like if it has a volume of 36 pi cubic feet, that means the radius has to be a number. Agreed? Now, we might need that. We might need to figure out what R is in a little while, but right now all I know is what the volume is at the instant in time. Now, I'm given some things, right? I'm given the rate at which what's changing?
The radius.
The radius, right? The radius is increasing at a constant rate. So the change in the
DRDT.
radius with respect to time, DRDT, should be 2 feet per second. And I'm looking for the rate at which the volume is changing, right? How fast is the volume changing? So I want dV dt. And exactly when do I want that? When am I looking? What is the instant? What's the information about what's happening at the instant?
36 pi.
At what's 36?
Volume.
volume. So at V equals 36 pi, right? I know the radius is changing at 2 feet every second. I want to know how fast the volume is changing at exactly the moment that the volume is 36 pi. Does this all make sense to everyone? Can I clarify anything? What now?
Now we have to find a formula for volume of a sphere.
Some equation that, well, it will be for the volume of a sphere, but when you think about equation, here's the way I think you should look at it. You're looking for any equation that somehow connects the variable here to the variable here. Why do I want an equation that has V and R in it? Why?
Because you're looking for V and you have R. Those
Yes,
are variables that you
derivative.
have.
So just forget this problem, okay? Forget this problem. Let's say I have an equation, it has V in it and it has R, right? If I differentiate that with respect to time, what am I guaranteed to see in that answer?
D of V and D of R.
dv dt and dr dt, right?
Yeah.
They will both appear. If I have an equation that has V and R and I differentiate with respect to time, neither one of them go to 1. So somewhere in that new equation, when I differentiate, I will have dv dt, dr dt. And so that will create the relationship, the related rate will be in there. So the equation we come up with can be anything that relates V and R together, but it has to fit within the framework of the problem. So I want to be looking at a sphere. Do I have something that goes with a sphere that connects the radius to the volume, right? So that's where we go and we look at our formula sheet, right? If we don't know the formula. And for a sphere, right here, the volume is 4/3 pi r cubed. Hey, that was the first question from the little quiz today, right? The little fake quiz. So I know that an equation that I can use here is volume equals 4/3 pi r cubed. That is a formula for a sphere that connects the radius and the volume together. Now I do implicit differentiation with respect to t on both sides. And so I get dv dt equals 4 pi squared. I'm sorry, 4 pi r squared dr dt. I already went over that when we discussed the quiz thing, right? So we all good with that? And now I'm going to write down over here dv dt equals 4 pi r squared dr dt. And I always like at this point to kind of just go through the different pieces and see if I have what I need to solve for what I'm looking for. So dv dt, right here, I'm happy to see it, right? I'm happy to see it because that's what I'm trying to solve for. dr dt, I'm happy to see that because I actually know what that is. That's 2. R, on the other hand, I don't know. At this point in time, we can go and find R though and plug it in here. All right, we can go use the instant in time to figure out what R is. So at the instant in time, my volume is 36, right? 36 pi, sorry. But volume is 4/3 pi r cubed. That has to be equal to 36 pi. Do you see how what I'm doing is I'm using the instant in time, the instant in question, this exact moment. And now that I've differentiated, I can look at this and I can say, okay, at that moment, what's the radius? I know the volume, what's the radius? So I just set the volume equal to the formula and now solve this for R. I'm going to do that down here. 4/3 pi r cubed equals 36 pi. To solve for R, I'll divide both sides by pi. Pi's are gone. I'll multiply both sides by 3 and divide by 4. Or multiply both sides by 3/4 if you like that instead. And I believe you get 27. R cubed is 27. Because you can take 36 divided by 4, you get 9, then hit it with a 3, you get 27. And now to get R, you take the cube root on both sides. Hey, when we do cube root, do you have to do plus or minus? Only square root, fourth root, sixth root, only even roots do you ever do plus or minus. If it's an odd root, you don't have to do plus or minus. So we only have one answer, 3. So now I know what R is at the exact moment in time. So I can come back here, dv dt equals 4 pi. Radius R, which is 3 squared, dr dt is 2. dr dt is 2, that was up here, right? Radius we just solved for. So that gives me, let's see, I'm going to square the 3, get 9. 9 times 2 is 18. 18 times 4,
72.
18 times 4, right?
Should be 72.
Oh, I thought I heard 32. I apologize.
No, 72.
72, okay. 72 pi, right? Should be dr dt, or sorry, dv dt. And now I need the units. The units for this answer. So I told you, just look at the thing on top first. This is V, that's volume. How do we measure volume?
In cubic units.
Cubic units, and our units here were feet, right? In this problem, everything was in
Yeah.
feet.
So
So
it'd be
this will be
cubic feet per second.
cubic feet per, now I look at time, T, and time was measured here in seconds, right? 2 feet per second. If this were 2 feet per minute, my answer would be my units would be minutes. So here, this is going to be seconds. There we go. That's my answer. So you have this sphere. It's growing, so its radius is growing at 2 feet per second, right? At the exact moment the sphere has a volume of 36 pi, I can tell you that the volume of that sphere is increasing at that instant at 72 pi cubic feet per second. It's important to understand that a second later, it's a different answer, right? Or even an instant later, a millisecond later, that rate of growth of volume is different. This is what's happening at an instantaneous moment. All right. Questions? Here we go. Same idea of a sphere that's growing. It's a different problem though. Let's see what the difference between this one and the one we just did is. All right, an expanding sphere. If the surface area of a sphere is increasing at a constant rate. Now the surface area is the area along the outside edge of the sphere. So we've got this weird situation where we have a sphere that's growing and the surface area is growing at a constant rate. I want to know if the surface area is increasing at a constant rate of 20 square feet a second, then how fast is the volume increasing when the volume is 36 pi cubic feet? So we know something about how fast the surface area is increasing. And we want to know about how fast the volume is increasing at a specific instant. Do y'all see how this is a major, like this is a very different problem than the previous one. Previous one, we knew how fast the radius was increasing, and we want to know how fast the volume was increasing. Here, I know how fast the surface area is increasing. I want to know how fast the volume is increasing. So our picture is going to look pretty much the same. We have a sphere that's growing. It has some radius, right? I have the instant time is where this sphere has a volume of 36 pi cubic feet again, all right? That's all the same. What's different here is what I'm given and what I want. right? Well, what I want's the same, but the given, what's the given here? So what are we given? Let me see. I'm going to go through. I have the roster today. Yay. All right. So I'm just going to kind of go off of what's first here. So Melina, how you doing?
Good.
Good. Can you tell me what I'm given in terms of a derivative of something?
From the question, sorry.
Mhm.
You're
So,
good.
so read this to me. If the what?
If the surface area of a sphere is increasing at a constant rate of 20 feet squared per
Okay,
second,
right there. Stop with that. So what's increasing at a rate?
the sphere,
The what of the sphere?
the surface area.
Okay, so you're telling me that the area is increasing at a certain rate of this, right?
Yes.
And you see this divided by this, like that's a fraction. It's like a ratio, right? So
Yeah.
it's here in this case, it's the speed at which something is happening. So I'm given that, right?
Yes.
So that would be d what over d what? The change in what with respect to time?
The dt over dv, if I'm correct.
What's changing? Tell me what's changing.
What's changing is the the surface area.
Okay, the area. The area is changing. So it should be the change in area, right?
Yes.
With respect to, so look at the fraction, 20 square feet per what?
Seconds.
Second. Second is a measurement of time, right?
Yes. So t.
So this should be dt on the bottom. Does that make sense?
Yeah.
Change in
Yeah.
area with respect to time. And you're saying that that should be 20 square feet per second. Yes?
Yes.
Okay. Everyone clear on that? All right. Ethan, what do we want?
Trying to find dv dt.
dV/dt, because we want to know how fast is the volume increasing, right?
Mhm.
So you want to know the derivative of the volume, the rate of change of the volume with respect to time. So we'll call that dV/dt. When do we want that, Ethan? Because there has to be a specific moment in time that we're talking about.
When the volume is 36 pi.
At V equals 36 pi. All right. We know how fast the surface area is changing with respect to time. We want to know how fast the volume is changing with respect to time at the exact moment that the volume is 36 pi. With me? Okay, now what do we need, Hunter? What do we need now?
We need our equation
Okay,
that relates these two variables.
yes, exactly. That relates area and volume. And we can look at this in the context of a sphere, right?
Yeah.
So do we have a formula that has area and volume in it together?
I found one.
You did? Where'd you find it?
I just looked it up.
Oh, you
I was
looked
sitting
it
there
up.
thinking about it, and I went, I wonder if there even is one. And I did find one. I don't know
Yeah.
if that's what you want to use, though.
Maybe we'll refer to it in a moment. Let's look
Okay.
at what we have. I mean, the only thing we know about a sphere is this, right?
Yeah.
I mean, that you'd have on your formula sheet. So
Which, and we can use those two formulas to relate. This is, we have the same numbers in them.
let me see. I'm going to go to a different page here. So here's all we have from our formula sheet, right? The first equation connects the variable v and r together, right?
Mhm.
So we have a relationship between v and r. So we have some relationship that goes back and forth between v and r right now with the first equation. And the second equation connects what two variables?
A and R.
A and r. So I have a way of getting from r to a, don't I, and a to r? So I
Yeah.
have a way of getting from r to a. So if there's a way to get from v to r and there's a way to get from r to a, then there should be a way to get to from v to a, right?
Yeah, I think we basically just want to solve that first one for R and then substitute that in on the second one, correct?
Exactly. So what we can do is we can take either one of these equations. Let's just take the first equation, V equals 4/3 pi r. You want to do the first one, solve it for R? Is that
Yeah,
what you-
because then we get it equaling A,
Okay,
which
so
is the number
let's
that we
solve
have.
this
So
for
we can
R.
isolate it.
Let's solve this for R. If we solve this for R, I have to do a couple of things. How about we do this? Let's see if you're comfortable with this idea. 3/4 pi times V equals R cubed. So essentially what I did is I multiplied both sides by 3/4 pi. 3/4 pi. And what happens here is the 4 and the pi cancel and the 3 cancels, and I'm left with the R cubed. And then over here, of course, I'll have a 3/4 pi in front of the V. That
Looks good
fair?
to me.
Okay, we almost have a R. Right now we have R cubed. So what will we need for just R?
You take the square, the cube root of both sides.
Cube root of both sides. Does everyone understand what we've done?
No, sir.
Daniel,
No, sir.
the look on your face.
Can you repeat it again?
Okay, so well, the whole point is this. We are trying to do a problem right now, right? Where in order to get the equation, we need an equation that somehow has A, the area of a sphere, connected to V, the volume of a sphere. Unfortunately, the only equations that we have are the equation that connects V to R and A to R. So what we're going to do is we're going to take one of them and solve it for R. Once we know what that is, we will plug that R into this equation, and we will have an equation that then has just V and R in it. So to solve this first one for R, we took the one in yellow, got rid of, I'm trying to get R by itself, so I got rid of this constant by multiplying by the reciprocal on both sides. That leaves me with just R cubed on the right. And then I've got this new fraction out here in front of V, and then just took the cube root of R on both, or cube root of both sides to get R. That make a little more sense? Now, unfortunately, and this is just, welcome to calculus. This is just, now we write the formula for A, right? 4 pi, and then what? R squared? R squared, but what's R?
R is all of that.
So I'm going to take all of that. And square it. This is what R is. So I just took that formula right there and I replaced that R with this. And that's what you're looking at here. And as ugly as that might look, that is an equation that connects A and V together, right? There's an A in here, there's a V in here. So if I can differentiate this, right, if I can, then I know I'll get a dA dt to pop out and I'll get a dV dt to pop out. Yeah, we haven't had to do this, right? First problem, circle, area, right? No big deal, formula is easy. Even the one before this, volume, volume is 4/3 pi r cubed. We didn't have to do any work to get the equation. Here we're having to do some work to get the equation. Now, I am not happy about this. I'm not real excited to differentiate this. Are you?
No,
So-
not really.
I'm going to rewrite it slightly. Just tell me if you disagree or not. I'm going to write this as 3/4 pi v times v raised to the 2/3. Now think of what I'm doing here. We had the cube root of something, right? And then we were squaring it. That's what that is, right? This was the cube root of something, and then we're squaring it. So when you take the cube root of something and square it, that's the same as taking that something and raising it to what power before you square it here? What's
2/3.
cube root can be rewritten as what?
What's up?
The cube root can be rewritten as what power?
The power of
1/3.
1/3, okay? And now you have something to a power So you multiply these two powers together, multiply, not add. 1/3 times 2 is 2/3. So this is the same expression, right? This is this.
Yeah, that looks a lot nicer to work with, actually.
That's gonna be, yeah, I think I'm gonna be okay with that. That's my equation. Back to the problem. All right, we good? Differentiation time. Derivative with respect to t on both sides. Left side is the one you're happy about, hopefully. dA dt, right? That's a derivative of a with respect to t. Done? Okay, 4 pi is a constant, right? It'll come for the ride. Times, okay, look at everything here in yellow. That is a chain rule. You have a bunch of crap here raised to the 2/3 power, right? So when you differentiate something to the 2/3 power, you bring your 2/3 out. And then it's all that crap, right? To what power?
Negative 1/3.
Negative 1/3, you subtract 1, right? Subtract 1 from the power. So 2/3 take away 1 is negative 1/3. Not done. Not done. Times. Now we're ready to take derivative of what's in here, right? Don't say product rule. I understand that's a product, but isn't all of this a constant?
Yes.
Okay, so I can write that as 3/4 pi times, now just take derivative of v with respect to t, which is
EV
dv over dt.
dv dt.
Sorry.
There we go. So as ugly as that may look, that is the derivative. That is my implicit differentiation. I'll run through it again. Derivative left side, dA dt equals 4 pi is a constant. Bring it for the ride. Now, chain rule on this. Power comes out, 2/3, subtract 1 from the power, boom. Now go inside. Oh, I've got a constant times a function. Bring the constant for the ride. Take the derivative of the function with respect to t, dv dt. We're finished. Now, oops. Now what I'm gonna do is I'm gonna look at this, okay? Come on, man, what's going on? I'm gonna look at this and I'm gonna see what I like, what I don't like. dA dt is given to us, 20, right? So this is good to see. dV dt, I'm happy to see because that's what I'm looking for. And luckily for us, V we know also, don't we? V is 36 pi.
36 pi.
All right. So I can just plug everything. I don't even have to go solve for, I don't need R at all, do I? I don't need R at all. Okay, so here we go. I'm gonna start plugging things in. The left side dA dt is 20. So we should have 20 equals 4 pi times 2/3. Then in the parentheses, 3/4 pi times V, but V was what? 36 pi? All raised to the negative 1/3. And then times 3/4 pi times dV dt, which is what I'm trying to solve for. So all I did there is replace that with that. I replaced that with that. And that was it, right? That's all I did. I believe some things are going to clean up significantly here. I do get a pi to cancel here and here, right? And then this and this cancel, and that gives me a 9 there. You all okay with that? I also see this 4 pi canceling with that 4 pi, and this 3 canceling with that 3. Pretty nice canceling happening here. 20 equals, let's see, the only thing I have left in front here is a 2. And then what's in the parentheses?
27.
27, right? 3 times 9, 27 to the negative 1/3. And then over on the back, the only thing left is dV/dt.
Sorry, how did you cancel out the 4 pi? at the
This
beginning?
4 pi here cancels with this 4 pi down here. Because you
Oh,
can look at that 4 pi up front as a 4 pi over 1. That good, Maddie?
yes, thank you.
Mhm. All right, I'm going to continue. I'll remind you that when you have something to a negative power, you can drop the whole thing down to the bottom, right? As a positive power. So this becomes 27 to the 1/3 instead of negative 1/3 dV/dt. But what does 27 to the 1/3 really mean?
3.
Yeah,
Root.
Cube
third root of
27, right?
27.
Which is just 3. So this is 20 equals 2/3 dV/dt. And I can multiply both sides by 3 and divide both sides by 2. And if I do that, I should get
30.
equals dV/dt. I bet, I doubt you felt that we would ever come up with a nice number like that out of this problem, huh? Like it would
No,
just come out to be something.
Not at all.
Yeah, it looked like there was no way that was happening, but it did. We got 30 as an answer. So our answer here, dV/dt, should be 30, and I just need the units. And volume is measured here in, let's see, feet cubed, right? Feet here. So feet cubed over our unit of time, which is seconds. So as you can see from this example, sometimes the equation is not, the equation that you have to take the derivative of isn't something that is just sitting out right there staring at you. Sometimes you have to work for it a little bit. And then the derivative obviously looks really, it looks like this was going to be terrible. Actually, it was not great, but it wasn't as bad as I guess maybe it could have been. Questions, comments, concerns, or gripes?
That was really interesting. I wasn't expecting it to turn out so nice.
Yeah. All right, let's keep going. All right, so I'm gonna let you read this, all right? And then I'm gonna call on somebody. Would you all agree that a picture would help if we had some picture of this situation, right?
Yes.
So this is where everyone's going to have a slightly different picture, right? Because we're all humans. We're going to kind of go about things our own way. So the way that I interpret this is that I've got a plane that's flying horizontally, right, over the ground. The plane is 2 miles high, and it's traveling 600 miles an hour, right? And it's headed directly over a ground-based radar station. So on the ground, there's a radar, and it's like headed directly over it, right? So it's not over to the side or anything. It's going directly, it's going to go directly over the radar station, but it's always going to be 2 miles high. So if I were going to draw this picture, I think what I could do is draw it from the side. So like here's the ground, right? And then this right here is the radar station on the ground. And then I have a plane that's flying through the air. So here's my plane. Anyone know what kind of plane that is? Is my
No.
drawing Not good
It doesn't
enough?
have propellers or any jet engines, so a glider.
No, there's a jet, there's a jet.
Yeah, I was gonna say, like, it looks like a fighter jet of some kind. That's the most I could
F-16?
get. Yeah, 15. Is it a MiG?
F-35 Lightning, F-22.
It's not a port, it's not a, it's a 22, doesn't 22 have 2 vertical stabilizers?
I don't remember.
Who cares? It's a plane, okay? If you want it to be a dot, make it a dot, right? Don't be intimidated by my drawings, okay? I've been drawing planes for 20 years now, okay? So don't let that turn you off. You can do this problem without being an artist like me. So there's my plane, right? And it's traveling horizontally. So I'm not going to draw a line, but I'm just to give a flavor. It's traveling in a straight line horizontally across. And one thing I can say about it is that this altitude is 2 miles, and that's never changing, right? Like that 2 miles is fixed. No matter where the plane is, it's 2 miles high. Okay, what else? The plane is flying horizontally. It's 2 miles high. It's flying over this radar on the ground. At the moment, I don't want to think about the moment yet. I do know that the plane is moving at 600 miles per hour, right? 600 miles per hour, miles per hour, miles per hour. That is a speed, that is a derivative. So that is the rate of change of something, right? The plane. I'm just going to notate that here. I know the plane is going 600 miles per hour, you know, that direction, let's say. Okay. Just trying to kind of put all the ideas down on paper first. Now, I don't have a single variable labeled at all on this picture, do I? Let's see, what are they asking? At the moment the plane is 6 miles from the radar station, right? At the moment the plane is 6 miles from the radar station, how fast, okay, all right, they want to know the derivative of something. How fast is the distance between them changing? I'm interested in the distance between them, right? That is changing throughout, like depending on where the plane is, the distance between them is changing. So I need to label that in my picture. Do we all agree that when we say the distance between them, we mean the distance from the plane to the radar station? That is the distance we're talking about. Yes? That is what I'm interested in. I want to know, like, it's almost like if we were connected with a rope. I want to know how that rope is changing as the plane flies over, right? Like if the plane was flying towards me, I would be bringing the rope in. And as soon as it went over my head, I'd have to let the rope out, right? We want to know at a specific instant how fast that thing is moving, that distance between us. So since that is actually changing as the plane flies, I cannot assign a number to it. I have to leave it as a variable. I'm going to call it H, because it kind of looks like maybe it might turn into a hypotenuse of something, but you can call it anything you want. I do recommend that you stay away from the lowercase letter d. And the reason is because if you want to know how fast little d is changing, you're going to go dt, which is kind of weird. It'll look like this dt. It just looks strange to me. You could use little d. I always avoid little d. All right. We okay? Picture-wise so far? In my other picture, with my plane and my radar station and the distance between them, in the fixed moment, what can you tell me about this distance?
That's equal to 6.
That it's 6 miles, right? That it's 6. So in this picture, this is 6. And do not forget, this is still what? 2. That does not
2.
change even in the exact moment. The 2 is constant. So in this particular instance, H is 6. Okay, we all good? All right. Destiny, is Destiny here? Alexander. Jake, Jake, I called you last time, didn't I, Jake? I remember calling you last time.
Yeah, but I mean, not really. You called on me and then you were like, wait, I already called on you the time before that.
Yeah, no, we'll go, let me move. How about Jackson? I feel like I haven't called on Jackson in a while.
Yeah.
Okay, Jackson. So I'm gonna ask you, Jackson, first, do you have any questions?
I don't have questions, but I am like slowly catching on to it.
Okay,
So it might take me a second.
that's fine. So in terms of, we're now looking maybe to see what we're given it or what we want. I'm gonna ask you to consider both of these. Can you, from the word problem, tell me either what we're given or what we want?
Well, we're given that it's at a speed of 600 miles per hour.
Okay,
So that
good.
it would be like d over dt in relation to.
Okay, good. Yes. You're on the right track. So Jackson, you know we're given 600 is the rate of change of something, right? 600 miles per hour. You know that, and you also even said that it's like d something over dt. Yes.
Yeah.
But you're not quite sure what it's actually measuring the change of,
Yeah.
right? Because that's not h, right? H is not changing at 600 miles per hour. H is not the speed of the plane. H is an imaginary rope connecting the two, right? So the struggle that Jackson's having in terms of what variable goes here is a good problem to have, because we don't have any other variables, right? Like, we don't have anything else. So here comes the critical point of the problem, all right? 600 miles per hour is the rate of change of the plane as it flies horizontally, right? So if I were to kind of visualize a right triangle upside down like this, okay? And if I label the distance from here to here as x, Jackson, you with me?
Yeah.
Then isn't the 600 miles per hour the rate at which that x is changing? Now,
Yeah.
Jackson, is the x shrinking or growing in my picture right now?
It's gonna be shrinking.
It's going to shrink, isn't it? Because as the plane moves from left to right in my picture, that x is going to get smaller. Yes?
Yeah.
So Jackson, can we say what d whatever dt this is now?
Is it just x?
Dx, yep, it's dx dt. See, but we had to assign that variable. We had to kind of come up with that on our own. Now, the other part is, Jackson, 600 miles per hour, that implies that it's a positive change, that it's growing, right? We need to put a negative on that 600 because it's actually shrinking. So let's just recap, everyone. We knew 600 miles per hour was going to come into play. It was a derivative, right? Miles per hour, we knew it was a derivative of something, but we weren't sure what of, because nowhere in our picture did we have a variable that we could say, oh yeah, that's changing at 600 miles per hour. Until we realized we have a nice right triangle like this. And if we call this side from here to here x, then we know that that x is actually shrinking at that speed. And so we call dx dt, right? That will measure the change in this x over time. We say it is negative 600, negative because of the shrinking of it. Yes?
Are we saying the plane is slowing down?
Nope, the plane's not slowing down. Okay, so look, if you were, just imagine you were standing right here, all right? 2 miles high, standing, floating in the air, and the plane's coming at you, right? Okay, so the plane is coming towards you. If you had if you were measuring the distance between you and the plane, is that distance growing or shrinking?
It's shrinking.
It's shrinking, right?
Mhm.
So x, that distance is shrinking, which means, well, how fast is it shrinking? It's shrinking at negative 600 miles per hour. Here's, Daniel, think about it this way. If you and I are standing there and we're throwing a baseball back and forth to each other, right? If I throw the ball towards you, right, it's moving towards you. Is that ball, does it have a positive velocity or negative velocity? Like isn't it relative? Like, for me, it's moving away from me, right? So it would appear that it's increasing in the distance over time. So that would be a positive speed. But for you, it's actually coming towards you. So is it positive or negative? Well, the distance is shrinking between you and the ball, yes? So it still has the same speed, but you look at that as being negative because it's coming towards you instead of going away from you. So this idea of positive and negative speed is all about your position within the physical situation. And because X measures this distance from the plane to that vertical line above the radar station, physically that thing is shrinking. So we look at it as a negative speed. I hope that makes some sense.
Yes, sir.
Yeah.
Thank you.
All right. Raquel, is Raquel here? Joshua, Mallet? Bethany?
I'm here.
Okay. Do you know what we want? What are we looking for in this problem?
We want how fast it's going. No, we want what's the change, the distance.
You want to know how fast the distance between them is changing, right?
Yes.
Okay, so what variable in this picture is representing the distance between them?
H.
H. So you want to know how fast H is changing, right?
Yes.
So you want me to write here what?
You
what?
want DH over DT?
Yep, exactly. Now, Bethany, when do we want that? There is a moment in time we're interested in. How fast is the distance between them changing? When?
When it's 6 miles from the station,
When it's 6 miles. It's meaning what?
the plane.
The plane is 6 miles from the radar station, right? In
Yes.
terms of variables, what are you referring to here?
When H is 6.
Exactly, at H equals 6. Now, you did all that perfectly, Bethany. Do you understand?
Yes.
Okay. We want to know how fast, good job. We want to know how fast the distance between the plane and the radar station is changing. So we want to know DHDT, how fast that's changing at exactly the moment that H is 6. And we've made it. We've made it to the point where we just need an equation, any equation out there that relates H to X. And maybe,
Question,
yeah, yes,
shouldn't that 2 also be taken into account?
It
The
may,
height?
maybe,
'Cause
so far we haven't needed it, right?
Okay, because I would argue just looking at our overall, that's a Y.
It is a Y, but it's not changing. Right?
Okay.
It's fixed. Emily, are you up? Are you there?
Yeah.
Okay, so Emily, can you think of any equation that connects the X in our picture to the H in our picture? Anything you can think of?
Like a squared plus b squared equals c squared.
Yeah, how about that? Does everyone see that? Look, just look at this triangle. Let's just draw that triangle again over here. Emily, what is, this side is a X, right?
Yeah.
This side is H. And what's this side?
It can be like, can it just be like any letter, or does it
No,
matter?
well, it can be a letter if you want it to be a letter. But in this particular physical situation, we actually know what it is and it's not changing. What is it?
Oh, 2.
2. See, Hunter, there's where it comes in. So that
Yeah.
2 that we saw here is actually this side of this triangle. And now, Emily, like you were saying, this is a right triangle, a squared plus b squared is c squared. What would that look like for this, Emily? Tell me what the equation would look like. What squared plus what squared is what squared?
Probably look like h squared equals x squared plus 2 squared.
Yep, x squared plus 2 squared is h squared. That's the Pythagorean, right? If you have a right triangle, a squared plus b squared is c squared. It's the 2 shorter sides squared added together equals the hypotenuse squared. There it is, which is just x squared plus 4 equals h squared. So I believe if y'all agree that Emily has produced for us an equation that connects h and x together that falls completely out of the geometry of this problem.
Hell yeah.
And now we can differentiate it with respect to t. And when we do it, we should expect to see a dx dt, and we should expect to see a dh dt, which is what we were hoping for. Okay, good. Daniel Patterson, you there?
Yes, sir.
Okay, so you get the differentiation of it. Or do you have any questions? I'm sorry, I forgot to ask if you had any questions.
I'll just figure it out as I go.
Okay. But you're good up to this point? There are no questions over what we've done?
No, I just need repetition.
Okay. So what about differentiating this thing with respect to t? How do you feel about that?
You would do 2x
Mhm.
multiplied by dx over dt.
Yep,
A constant would just be 0,
yep.
and then equals 2h times d of h over dt.
There you go. There's our derivative. Implicit differentiation. We had to do chain rule on both the x squared and the h squared, of course, derivative of 4 is 0. So cleaning that up just a little bit. I could, if I wanted to, and why not, divide both sides by 2, just to get rid of it. All right, just get it out of there. Which gives us kind of a final equation to work with here. And I'm ready to kind of look at this and see if I've got everything I need to go ahead and answer the question. So right off the bat, I actually don't know what x is. Like explicitly, it's not written out anywhere here, is it? What about dx dt?
Yeah, that's negative 600.
That was given, negative 600. How about h?
Six.
Now we can fix it, right, at 6. So we're okay there. And dh dt, well, that's what I'm looking for, right? So all that's good. The only thing I really need to figure out is x. So where do I get x from?
We can solve for it using h equals 6.
Yeah, so now that we can fix everything in time, if we go look at this same triangle right here in this picture, with this being 6, this being 2, and this being x, I should be able to solve for x, shouldn't I? Using the same good old Pythagorean that we did over here. So I'll do that down here. I know that x squared plus 2 squared must be 6 squared. So x squared plus 4 must be 36. So x squared must be 32. So x must be the square root of 32. Now I should do plus or minus here, but x is a distance on a triangle, so I'm only going to look at the positive answer.
It's 4 root 2, if I remember correctly.
Yeah, you can do a little more with that, right? I'm going to leave it as root 32 because it really is not going to matter in the big picture here. I've never been a big fan of simplifying radicals because, yeah, I mean, square root of 9, yes, square root of 9 is 3, but the square root of 27, the fact that that's 3 root 3 really doesn't make a huge big, difference in the big scheme of things.
Simplifying
Okay.
a radical into a smaller radical just leaves you with more radicals.
Yeah, you still have a radical, right? You haven't avoided anything. Okay, so now I replace x is root 32. What was dx dt? Wasn't that negative 600?
Yeah, negative 600.
Then equals h, which is 6, and then dh dt is what we're solving for. I can divide both sides by 6. I get negative 100 root 32 equals dHdt. Just divided both sides by 6. Move the negative 100 in front of the root 32. And I think I'm just going to get on my calculator and get a decimal approximate.
Shouldn't that be 2 dHdt?
Where? What?
Oh, wait, no, I see what you did.
Oh, the twos I canceled a long time ago. Is that what you're talking about?
Yeah, no, I forgot about that you canceled those
Yeah.
out.
You would still get the same answer, of course, because you would have a 2 on both sides. So at the end, you should have the same thing. All right, so on my calculator, I'm going to go ahead and do the square root of 32. And I'm going to multiply that times negative 100. And I get dHdt is approximately negative 565.7. I'll just round one decimal place. What per what? So H is measurement of the distance between the two. How are we measuring distances in this problem?
Miles.
Miles over the time measurement here, which is hours. Or miles per hour, right? Same thing.
To be honest, wasn't expecting use of Pythagorean theorem.
Yeah.
Not looking at it.
Mhm.
Could we have used SOHCAHTOA or tangent to be specific?
Good question. You don't know anything about any angles, right? So like SOHCAHTOA, sine opposite over hypotenuse, that'd be great, but it's sine theta is opposite over hypotenuse. So you don't have any information about the angles here, do you? So you'd probably want to avoid that because then you're introducing variables that aren't even in your picture. Now, I'm glad you asked that question because of the next question. It's the same problem, but I'm asking you for something else. So why don't we do this? I'm going to put you in breakout rooms. Let's see if y'all can't figure this one out. Or at least get it to the equation. You should be able to fill this table out. Hopefully, your picture is going to look really similar. I'll give you a moment to take a picture, screenshot it, write it down, whatever. Same plane, 2 miles high, 600 miles per hour, going over radar station. I'm talking about a moment where the plane is 6 miles from the radar station, same 6 across. But instead of asking you how fast the distance between them is changing, I'm asking how fast the angle of the tracking radar station is changing. So I'm talking about an angle, when you're looking at the plane go over, right? There's an angle in there. I want to know how fast that angle is changing. So Daniel, I think your idea there is going to come into play here because now the angle is what I'm asking for, the change of the angle. All right, let's do some breakouts, see how it goes. Let's see, it's 10 after 2. There are going to be 3 to 4 of you in each room. I'm not sure how far I'm going to let you go with this. Maybe just 10 minutes, just so you can talk about things, maybe come up with the equation. There you go. Enjoy. Okay. So I tried to visit each of the breakout rooms just to get a feel for how things were going. I know it's hard in a breakout room to really be productive without being able to look at each other's work and, show each other what you're drawing. So first thing I'm going to say here is that everyone could kind of draw this a different way, depending, depends on how you wanted to do it. So this is the way I did it. I said, all right, got a plane, got a radar station. I've got the distance between them. I'm going to call H. And then this right here is theta. Between theta is from the ground to the line pointed to the plane. And I called this X because dx dt changing it at 600. This is the same exact picture as this picture, with this being X, this being 2. And dx dt is still changing at -600. I guess what I'm trying to say is that this moving across, X changes at -600, is the same as the shadow of that plane straight down, and then moving across, that would also change at -600. Either way, no matter which way you kind of position the triangle. Does that make sense or no?
That makes sense.
So that's the way I did it. I drew this picture.
That's what I did.
And then over here, I said, okay, at this particular instant in time, 6 is the distance between them. 2's here, theta's in here. Don't know what it is yet, but I could figure out theta, couldn't I? Could I not figure out theta right here if I needed to?
Yep.
I have two sides of a right triangle.
Yep.
All right.
SOHCAHTOA and then taking inverse sine.
Yeah, do something with the trig function and then go solve for theta. So here, dx dt is 600. That's the speed of the plane. That's how fast x is changing. D theta dt is what I want, and I want it at the moment that h is 6. So now I need to somehow connect, and this is important, x to theta. I need to connect this to this.
Would it be the cosine definition?
Yeah, so I have a lot of options. So let me tell you why I'm not going to use a few of them. I'm not going to use this. I'm not going to use x squared plus 2 squared equals h squared. The Pythagorean, I'm not going to use that. Why? What don't you see in here?
Theta.
Theta, and I need theta in there, right? So it can't be that. Theta connected to x, I could connect theta to x and h. This is the adjacent side, that's the hypotenuse. What trig function connects adjacent?
Cosine?
Yeah, that's cosine definition.
So isn't cosine of theta equal to the adjacent x over h?
Mhm.
Right? That's true. I'm not going to use that one either. Why? I will get it. Look, I've got theta and x in there, right? So I will get a d theta dt. I will get a dx dt, right? But what
Yeah.
else will I get?
You got a quotient rule.
So there's an h in here also. So I'm also going to get a what? I'm going to get a
Uh,
d dt. I'm going to get dx dt, but I also will get a dh dt.
DHDT.
And do you
Yeah.
have any information about dh dt? You know
No.
nothing about dh dt. You don't want it. You're not giving it, right? You don't want to mess with h because h is something you don't know about.
So when you said we can choose any equation we want, so we really are trying to find an equation that only has the information but not too much, kind of then?
Well, any equation, you can choose any equation that connects these two together, right? But it is possible that you use an equation that has more in it than you have information to support. Like, I don't know how fast h is changing with respect to time. And I know when I differentiate, I'm going to have a problem there. I'm going to get dh dt.
So question. So we couldn't substitute the h in before we differentiate?
No, good question. You cannot replace h with 6.
All right,
And the
because
reason is-
that's what I did.
Yeah, So here's why you can't do that. Remember when I was saying last time, imagine that I'm running, right? And then I say, okay, freeze. And I say, how fast am I going? Well, if you freeze it, you can't talk about how fast something's going.
Gotcha.
You can only freeze after you've taken the derivative.
Gotcha.
So I can't do that.
So we want to use the tangent formula then.
Tangent of theta, let's see what that would do. Tangent of theta would connect the opposite over the adjacent. That would be 2 over x. And that I like. It has just theta, just x. I'll get d theta dt. I'll get dx dt. That's the one I want. That should look somewhat familiar to the second problem I gave you today on that little fake quiz, right? Except instead of tangent theta equals 1 over x, that was a quiz, it's now 2 over x. Yes? Now, I realize some people may have drawn this a different way. So after I finish this, I'm going to ask someone to tell me how they drew it, and then we'll do the whole thing again, and we'll see if we get the same thing. So I'm going to go, equation is tangent theta equals, I'm going to write it 2x to the -1 instead of 2 over x, because I'm just setting myself up for the differentiation. Here comes the derivative. Secant squared theta times d theta dt equals -2 x to the -2 dx dt. So I just used power rule over here. -1 came out, subtracted 1 from the power, took derivative of x with respect to t. I'll go one more line here. I'll drop that x squared down. There we go. I like that. Now let me check it to see if I have everything I need to solve this. I'm gonna go after the things I know for sure I'm happy with. D theta dt is what I'm looking for. Dx dt is what I'm given. We have a little bit of a problem though. X, do I know what X is at the instant in time?
No, but we could solve for it.
Probably figure out what it is though, right?
Yeah, because we have at the instant, we have 2 and 6, so we can
Yeah,
use
at the instant
Pythagorean.
picture.
Now you use Pythagorean.
Yeah, I can use Pythagorean to get the X, right? But don't I also need theta?
Yeah, but we can find the secant of theta given x and 2 once we find x.
Yeah, let's go get X. Okay,
You
let's
don't-
go get X.
Yeah, because
So-
technically we don't actually need to find theta itself, just the secant of theta.
That's right. We don't need theta itself because we're really looking for secant of theta. So let's get the X first. I'm just going to do Pythagorean on this. This will give me, didn't we do this earlier? Square root, wasn't
Yeah,
it
square root of 32.
So X was root 32. So basically my triangle looks like this. I have 2 here, I have 6 here, and I have root 32 here, and I've got some angle in here. I would like to know what secant squared theta is. So I'll remind you, this really means, right? This really means secant of theta squared, right? That's what secant squared theta is. But secant of theta, if you go back and, well, cosine of theta is adjacent over hypotenuse, right? Cosine is adjacent over hypotenuse. So secant is its reciprocal. So instead of adjacent over hypotenuse, shouldn't this just be hypotenuse over adjacent? Whatever that is squared.
6 over root 32.
Yeah, so your hypotenuse is 6 and your adjacent side is root 32. So this should become 6 over root 32 squared, which is 36 over 32. There's a reason we took pre-cal, I guess, right? Here we go. All of this down here. The secant squared theta I just determined was 36/32. Oh, wait, we never got, oh, we did get X, never mind. D theta dt is what I'm looking for. That must equal -2 over, okay, what's X squared?
Just 32.
Is 32. And then times dx dt, which is -600. I need to solve for d theta dt, so I'll multiply both sides by 32/36. I'll do that here and here. And here it's like that, they go away. So I get d theta dt equals over here, luckily for us, the 32s cancel. I get 1200/36. I just multiplied straight across here. And that reduces, I'm just going to get the decimal answer of this. This is about 33, well, exactly 33.33 repeated. So my answer is d theta dt equals 33.33, and now the units. So this can be a little tricky, all right? Theta. Degrees or radians?
Degrees.
Why degrees?
Because
Theta is represented as a degree.
yeah, this
Never in this problem did I say it was degrees or radians, did I?
yeah, but 33 degrees makes sense given the triangle versus
Yeah.
33 radians, which would be a couple of circles.
That's right. The answer is radians. It has to be radians, all right? Everything is radians unless you specify degrees.
Is it really?
Yes. So this is going to be radians. I'm just gonna put rad per time. What was our time measurement? Hour?
Hour,
so-
I think, yeah.
Yeah, so I know, like you said, 33 radians is a lot of revolutions, but it's per hour.
Gotcha.
So-
Right. Yeah,
so-
I forgot this is the measurement of movement, not the measurement of the actual angle. Right. Okay. I didn't realize that. I kind of figured we'd default to degrees, not radians.
You default to radians and then convert to degrees if you need to.
That's an awful conversion.
Yeah. All right, we only have 6 minutes. Did somebody draw this triangle differently? I know someone had to have. Everyone drew it that way?
No, sir.
Mine
The
was
same
just
way,
like that.
the same way as the previous problem.
Okay,
Yeah,
so
except
let me
the
do it
X is
that
on
way.
top.
So like this. And then bringing that triangle across like this. And having X here, this is H and this is 2, yes?
I even use the same colors, yes.
Yeah, like why overcomplicate and try and fix what you got in front of you?
So where's theta in this picture?
In the bottom right,
Right here?
no, sir, the other side right there.
Right here? Okay,
Yes, sir.
so what about this? Should we get the same answer?
Yes, sir.
Looking at the rate that that's changing, right? The rate that that's changing compared to the rate that what I just did, I found the rate that this was changing, right? That's going to be in my picture, theta's growing, right? Yes. And in this picture, theta would be doing what?
It'd be shrinking. That's what I
Shrinking.
told Ethan in the first, when we were in the group. I was
Mhm.
thinking of where we were gonna put theta in.
Yeah, well,
It
so
can either
the
be
only
growing or
difference-
decreasing.
this goes back to what I was talking to Daniel about. If we're throwing a baseball to one another, right? you can look at this angle as being, oh, this angle is growing by this much, or if you're on the other side, it's shrinking by that. It's really just a measurement of how quickly that line is rotating. So it's completely okay to do it this way. What would the trig function be that connects these together? You need to connect theta and x. So here's theta, you need the x and then use the 2, which would be what trig function?
It'd still be tangent, wouldn't it?
Tangent.
It'd be tangent, but it would be actually nicer. It'd be tangent theta is x over 2, right? Tangent is opposite over adjacent. So I'm almost out of time, so I'm going to crank through this really fast. If I differentiate this, watch what the differentiation is. Secant squared theta d theta dt, that's still the same. But on the other side, this is really like 1/2 x, right? So that just becomes 1/2 times the derivative of x with respect to t is dx dt. I like this formula.
Yeah, that's a much nicer one to work with, to be honest.
This is actually real nice because in order to solve this, oops, that's not what I meant to do. I only need to know one thing, right? To do this. One thing I don't have, right? D theta dt is what we're looking for. Dx dt we're given, right? And this right here, secant squared theta, would be the only thing I need to do. On our triangle, let's just make sure everything would be the same. If we redrew this triangle over here, this would be 6, this would be 2, this would be x, right? Wouldn't x still turn out to be root 32? Here's theta. So this is root 32. What is secant in this picture? Cosine is adjacent over hypotenuse. So what would
Be 2/6.
2/6 would be
2/2.
cosine, right?
Yeah, so secant would be 6/2, so 3.
Which is 3, right? Which is 3. So this should be 9, shouldn't it be? Yes, 9. I know I'm going fast, I'm almost out of time. What's d theta dt? Don't know. Equals half of what's dx dt? Speed of the plane.
600.
Negative 600.
Negative 600. Divide both sides by 9. So you put the 9 over here on this side with the 2, you get 18. And what do you get? Negative 33.3.
That's so much easier.
The angle's shrinking there, right? The angle is shrinking in that picture. Both of those would be correct, okay, in terms of if you drew your picture this way, then yes, I understand what you're saying. This theta is shrinking at this rate. If you drew your picture the way I did, then I understand your theta is growing, so your answer can be positive 33. But you can see, well, hopefully you can see from those two examples, one way was a lot easier than the other. And there's nothing really that's going to indicate that when you're doing the problem, which way is easier. And not every problem is going to have more than one way of doing it. I hope that in the last, day and a half of talking about this, that you're starting to understand why Cal 1 students do not like related rate problems.
Oh, yeah, I understand entirely.
There's just a lot going on here, and we're still, I mean, last time I said we put our toes in the water. All right, now we're up to like maybe, mid chin, okay? Like there's so many different types of problems that you can do here. This can get real messy. So I think what I'm going to do is I'm going to say at this point, I'm going to cut you loose on the homework, okay? I recommend though you try the problems to the best of your ability before you go looking at my homework video solutions. Don't just watch my video solutions and be like, oh yeah, I would have come up with that. Yeah, no problem. I get that. Like the whole part is, can you do all this stuff? Fill out this table. Can you create this on your own? The geometry. Can you, I mean, there's still stuff I haven't done. I'm gonna need more time for this. We haven't seen anywhere where we've needed any other formulas like other geometry things like similar triangles. We haven't needed to call on anything like law of cosines or law of sines. There's all sorts of geometry that can come up here. So yeah, do what you can with the homework. We'll come back, do some more, but eventually we have to continue, we have to move on. All right, we can't. If it were my choice, we would spend 3 months on just related rate problems, you know? I mean, we could technically do that, but the
Yeah, I
train
can
must
see that.
continue. The train must continue moving. All right, everyone,
So just do as much of the homework as,
do as much
as
of the homework as you can. And
Gotcha.
refer to the homework video solutions if need be, or reach out to me. Daniel, you're not happy? Yeah.
just looking over and seeing the little sad.
That was perfect, dude.
Yeah, I know. I mean, it is what it is, man. It's the word problems along with, I mean, there's nothing off the table now. Like stuff that you learned in pre-cal and different relationships and things, it's all on the table here. It's all in full display. So we could have something get pulled out of pre-cal that you don't remember because it's been so long, right? Some weird obscure formula. So I understand this is challenging, but it's also rewarding. If you can figure these things out, it's very, very rewarding. All right, do your best. Come with questions next time. Have a good weekend.
You have a good weekend. Thank you, sir.
Thank you, sir. I'm gonna try to understand this.
Yeah, I know.